Hi, in this video I will tell you about raw CEL files, how to use them. You might need it when you do microarrays yourself, or you try some publicly available data in GEO2R and you do not like what you see. Sometimes you do not believe your eyes how ugly it looks. Then you might say, I'd like to try raw data and do all steps the way I'm used to. Previously I showed you one case of strange microarrays where data distribution were pretty weird and it was fixed by filtering negative values. Here is another example where you see that something is strange happening in MA plot, and if you look closer to this slide, then you see that all data are zero-centered and very narrow. These are double data for microRNA arrays and gene expression arrays, and in both cases they are zero-centered. What's going on here? The explanation could be that either authors did some ratio taking samples divided by unknown control, or more likely it is a scaling applied to a data. And what scaling is literally that you rescale all the expressions to some common scale. It is often used in heat maps, actually always, nearly always. It's pretty usual in RNA-seq data analysis, but not here. And more you can read in Wikipedia for feature scaling and find out that there are at least 5 different. I will not stay on it. Here I will explain you that if you do not like what you see, then you better go to a CEL raw data and incorporate them into your limma GEO2R protocol. So it's basically limma with some lines for GEO2R. The trick is that you use justRMA function from library AFI, which reads the raw CEL data and generates very similar data type ESET, which can replace GSET in your protocol, and things will go smooth and easy. Before you open RStudio, you have to do a few things. First, you visit the NCBI Geo, dial this number, then you download this raw tar file, and then you get this raw tar file on your computer, move to a place you want it and untar it, and then you will see a series of CEL files GZ compressed. Then secondly, you can do a bit of GEO2R analysis. You define groups, doesn't matter much how you define it, and run the analysis. And after it's done, you copy paste the R script. The most important part is, of course, the beginning of it, where you will learn how you import data into your RStudio. It will be original scale data, but anyway. And then at the end, you might borrow some illustrations. The middle part will be considerably modified and changed according to the limma user's guide. Now we are ready to analyze the data. First we import AFI and limma. Then of course you place your raw CEL files, list the files. Here we are. And now we use this famous justRMA function, where in one line we generate ESET. Structurally, ESET looks very much like GSET generated by getGeo function. It has also assay data, phenodata, feature data, everything. Only for features it's not much. So let's investigate a bit. Here are the numbers instead of gene names. The column names are inherited from CEL GZ files. The minimal value here is 1.5. It's okay. These are the column names, which are good to generate a sample table. Here is probably a good time to explain the experiment. Authors injected newborn mice with either sodium chloride or the virus, and then waited for 3 days, 7 and 14 days. That's what it is here. NS is for saline and NRV is for virus. And then they isolated bile ducts and did RNA extraction and analysis of microarrays and the gene expressions. So all this information is already in column names. Therefore, we extract it by string split and generate in a few steps. Sorry, too fast. And then we generate a nice table where everything is clear, the batch, the treatment, and the day. And we give all these names to the samples. Now, when we do histogram, we see that data are log transformed, and box plot reveals that samples are already normalized. Now let's check what else we have to do. We have this problem that gene names are not really gene names, and therefore we need original data from GEO2R for the proper annotation, and why not for comparison of this data with the scale data. Therefore we continue with the GEO2R lines. These are from GEO2R. Then again we check, did we import it right set? Yes, it is a scale data. What are the row names here? The same. The annotation is now more diverse and includes real gene names. Again, we have a problem, number one, that column names are not identical, and in addition, the dimensions of the data sets are not the same. So number of genes, which are features, differs in E set and G set. And in order to replace one by another, everything should be the same. So how to do it? We do it in 4 steps. First we say, let's get G set only those row names which are in E set. Then we say, let's get E set only those row names which are in G set. And therefore now the features in E set and G set are the same. And now we have to make equal headers for column names. So E set column names are the same as in G set. And now we are ready to replace one set by another, but we will skip this step for a moment. Why? Because we also want to compare the data. And in addition, we add date and treatment column to simplify our design wishes. So it's simply convert 2 factors into 1 factor, after which we have a day treat, like day 3 control, day 3 virus, 7 control, 7 virus, and so on. Now we say the design will be 1 factor of this composite day treatment. No, 2 factors plus batch and 0. Then we run lmfit and then plot assay. This is a horrible assay plot. Why? Because data are scaled. It's all in the center. How well limma functions can process such a data, I don't know, but we can see it in comparison later on. Next, we check again column names after the fit, and we do quite elaborate contrast. We say, let's take those expressions which differ from day 7 and day 3 for wild type and the viral type, which we call MT, and they take a difference of those two. Limma is beautiful in this respect. And then do a contrast fit and bias and the summary. And the summary is also quite nice. It says for the control wild type we have down up these genes, for the viral infusion we have those, and here we calculate the difference, what we want. And then we finalize it, getting the final tops table and order, and so on, so on, so on. And then we write the result. These are scaled data, so let's put it here, scaled, and save it. And then we go back to the number 4, and then we say replace gset values by eset values. And then we basically repeat all the lines without any change. Now assay plot looks finally as it should. And then do the same contrast. It's comparable numbers but less. Go to tops. And now we say row. After we saved those data for scaled and row, we can compare those results by Venn diagram. Say scaled and row are those from tops. Define the list, ask for ggven, and now we see that scaled data give approximately 25% more expressed genes than in a row set. Why? Because limma relies on dispersion analysis of the data, and scaling makes it worse. To summarize our experience, was it worth it to use a raw data instead of scaled? And the answer is yes. Scaled data give a disturbance in the analysis and better not used. You can also experiment with the heat map and see how different are scaled data from raw data. Strangely, scaled data still need rescaling for a proper heat map, but this is rudimentary to the major question. What to do with the scaled data and how to replace it with the raw data, and I hope you got the idea.